If there's any repeats, it's 0. There's exactly n factorial such terms. There's n factorial permutations of the numbers 1 through n. And so there's n factorial non-trivial terms in this multi-sum. So for n equals 3, you get epsilon 1, 2, 3 equals to epsilon 2, 3, 1 equals to epsilon 3, 1, 2 versus epsilon 3, 2, 1 equals epsilon 2, 1, 3 equals epsilon 1, 3, 2 equals minus 1. These are the 3 positive terms, and these are the 3 negative terms in the cross product. You can use this epsilon ij symbol to define the cross product like this. A cross B, you can write as the sum ijk of epsilon ijk ai bj x hat sub k. This is a stone-cold formula for the cross product in calculus 3. And it has the same guts, the same non-trivial terms as the determinant. That's why the determinant mnemonic works like it does. It's the same anti-symmetrized machinery. So, but do you see there's something special happens here, which is that there's 6 terms, right? So for a 4, so let's just think about it for a 4 by 4 matrix. For a 4 by 4 matrix, this sum has 4 factorial things. Or if you want to think about it in terms of the recursion, it's 4 3 by 3 matrices, which is 4 times 6 plus 4 times 6 plus 4 times 6 plus 4 times 6 factorial. I mean, it's 24 is what it is. 4 by 4 has 24 non-trivial terms. So the 24 non-trivial terms would have to correspond to 24. If you had a 4 by 4 matrix, you have to find 12 lines like this, and 12 lines like this. And so no, there is no nice way to do it. Yeah. Now I started like a solid 5 minutes late, so I'm just going to go a little bit over today because otherwise I'm cheating you guys. I'm sorry, but I wish I could start class on time. I really do try to get here, but this 15 minutes between class just doesn't really work, does it? Sometimes, not really. You guys should complain. I didn't tell you to say that. Who should you complain to?
Jerry himself.
You should complain to his dad. No, I'm just kidding. Your dad has no such power.
Yeah, the faculty senate doesn't have really any power.
Yes, the faculty senate is...
Jerry himself.
We complained to Jerry himself.
What's your dad teach?
Sure. Differential equations. Look away! Oh man, that's not what we want. All right. The best thing for us to do, actually, if you'll forgive me, is to look at my 321 notes. My 321 notes for determinants are pretty good. I should probably post this for you. Because the advantage of my 321 notes versus there's a chapter on determinants in the notes I posted for you guys. It's actually better for you to look at the 321 notes for here because I've revised it to emphasize the role of volume in determinants, which is important. So I will post this for you guys. If you want to read something other than the book, you're welcome to. But here I actually work out my stupid, there it is. So I showed you the 2 by 2 case, right? But you guys have also studied the triple product in calculus 3, right? So here's actually a picture for a slanted parallelogram that shows why the formula AD minus BC really does give you the area of the parallelogram. You can shift these triangles around, blah, 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 blah. I'll let you look at it. But in calculus 3, we learned this triple product rule, which is that the volume of a parallel pipette with edges, the red one, the blue one, the green one, it's given by A cross B dot C, plus or minus. And that's exactly, in terms of formula, the same as the determinant of A, B, C glued together. It is the volume of the parallel pipette with sides A, B, C. Where the sign, if you do A crossed into B, if it's in the same direction as C, the determinant's positive. If you do A crossed into B and C is in the other side of the right-hand rule, the determinant's negative. So the determinant picks up on the orientation, the right-handedness of the vectors ordered column 1, column 2, column 3. If the third column is on the same side as the right-hand rule to suggest from the first two positive determinant. Otherwise, it's negative, in illustrating the fact that you're looking at a left-handed triple. None of that helps you calculate. I'm just giving you some motivational jibber-jabber. So anyway, there's my formula. Here's actually the details for the 3 by 3. Who cares? Here's what you want. Here's what he wants. Here's what you need. This is the 3 by 3 formula. Here's the 4 by 4 formula he was talking about, recursion. So across the top row, I do A times everything that's not here, right? F, G, H, G, K, L, N, O, P. I will post this so you guys don't have to write it down, okay? And this is already in the notes I posted, but I would like for you, if you're going to read my notes, read the chapter in the linear algebra notes. It's been edited. It's better. And you can ignore any threats about proving things. That's for the other crowd. See here. You guys are my friends. I trust that you already could prove them. You don't need to show me you can prove it. I just trust you can. So let's see here. And then minus B. And then so like E, I, M, G, K, O, H, L, P. That's everything that's not in the B row and column, right? We get to C. C, we scratch that out and that out. It leaves us E, F, I, J, M, N, H, L, and P. Right? And then each one of these is a 3 by, it's quite awful, right? There's 24 non-trivial terms for a 4 by 4. 5 by 5 determinant. 120 terms you have to add. Keeping track of the delicate balance between plus minus, 60 pluses, 60 minuses. One that you get wrong, it all falls down. Yes?
I remember when you had us calculate the Jacobian for a 4 by 4 matrix. Cylindrical coordinates or spherical coordinates. It was like 6 pages long.
I did that, didn't I? Yeah, in his calculus 3, I had them calculate the Jacobian of the hyperspherical coordinate system. It's got 3 spherical angles, and it has very little sparseness in the matrix. Sparseness is zeros. Zeros we like. Let me show you why. So like, here's why we like zeros. For example, this one. See that? It's like what you want to do is you want to pick a row which has got mostly zeros, because then when you expand, that means that when I expand across the second row, what did I do? I expanded on the 4th column. I chose that one. All right, sorry. So on the 4th column, plus, minus, plus, minus, plus, minus, plus, which you can also get by minus 1 to the 4 plus 4, because that's the 4, 4 spot. So when we have the determinant of this one, I'll expand on the 5, because that's got mostly zeros, see? So I do 4 times 5. 5 is in the 2, 3 spot. That's why I have minus 1 to the 2 plus 3. That gives me the sign. So I can either look at signs by making a chart like this, or I can go, I'm looking at the ijth component and expanding there. So I do minus 1 to the I plus j. That gives me the plus or minus in the cofactor expansion. So I guess that. And then I'm to a 3 by 3, which then I'll use the stupid trick, which I don't know how to tech, so I just say it in words here. But I'm talking about the thing that's about right here. So I did that, and I got 500. And as you can see, I did not add and subtract 120 things here, right? Most of those, thankfully, were 0. And by judicious choice of the expansion of which row I'm doing, I can shortcut tons of calculation. Let me show you another one. These are the properties of the determinant. I mentioned to you the transpose doesn't hurt it. Here's another one that's awesome. If you see a row of zeros, game over, determinant 0. If you see a row repeated, the determinant 0. If you see a column row repeated, if you see a column repeated, determinant 0. If you see a row repeated, the determinant 0. Beautiful. You can do row additions. It doesn't change the determinant. Like if I do this kind of a type 3 operation on the determinant, it does not change the determinant. If you do a row swap, you change the determinant by minus 1. Yeah?
So does that mean in some cases it's more efficient to like do row reduction before you...
Goodness. Great googly moogly. Yes. Let me show you a problem from my linear algebra test to help you appreciate the importance of what you just said. Now, here's something that will catch you guys off guard if you're not looking for it. The determinant of k times a is k to the n times the determinant of a. You get one copy of k from each column you pull it out of. So we have like this linearity in each column. So I can break up linearity in each column like one at a time. The other fun fact, the determinant of a diagonal matrix is product of the diagonals. The determinant of a triangular matrix, product of the triangular, the diagonals. If you have a block matrix, this is important. So a block matrix, if you have a block diagonal matrix, the determinant of a block diagonal matrix is the product of the determinants of the blocks. So simple. So like determinant of M is determinant of A times determinant of B. This is very, very simplifying, right? And then, so here's an example of the technology I was just talking about. I've got 8 and 6, right? So if I column swap, then I get 6, 8, 1, 1, 1, 1. The thing is, we know the determinant of a diagonal matrix is the product of the diagonals. So then once I have a diagonal, multiply, done. This one here, column of zeros, that has determinant 0, but then I look for the solution to this thing. That's more interesting. These things, these values I'm finding, these are the eigenvalues. There's Kramer's rule. Tell you what, I'll talk about Kramer's rule next time. And there's also, Kramer's rule is pretty awesome. Finally, there is a formula for the inverse of a matrix in terms of what's called the adjoint. A inverse is 1 over the determinant of A times the adjoint of A. The adjoint of A is formed by taking all of the cofactors and sticking them in their own matrix. So like for the 3 by 3 matrix, it's quite awful. I'll actually derive that stuff for you next time. I think it's probably important for you to see it. So what if I'm a little bit behind my schedule? I think I've told you enough that you can do determinant problems after today. Yeah, but we'll still do a little bit more next time. So here are the cofactors: 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, like so. This is the adjoint matrix transposed. So these are all those cofactors. So that divided by the determinant of the A, B, C, D, E, F, G, I. There you go. Seems like a fitting way to end today. Well, I want to show you that example, then I'll stop. But this right here is the inverse for a 3 by 3 matrix. This is the formula for the inverse of a 3 by 3 matrix. I always, anyone I show this to, I try to emphasize, I am not asking you to memorize this. Do not memorize this. I'm showing you because you can. I want you to be aware of it. But this is not me telling you this is how you're supposed to calculate it. Understand? Are we clear?
And Min memorized it.
Min memorized it. And I had 2 people in 321 do it this semester. It's bizarre. I haven't had it happen in like a long time. But for this semester, for some reason, I had 2 people do it. It's easier.
I feel like the row reduction would be easier than that.
Row reduction is definitely easier. It's way, way easier. Yes. It's much, much faster. So here's the test I gave in linear. Don't worry. This is probably not a reflection on, oh, I shouldn't show you these. Some of these I may have just made you do. Did I?
I don't mind seeing the answers.
You don't mind seeing? I do have a solution to the quiz. I got to go scan it and post it for you guys. If I don't, please harass me. So this thing right here looks scary, right? But if you do row 5 minus row 1, it clears those zeros. And then you just got to say, oh, wait a minute, I just need to like swap these 2 and then swap those 2, right? And then diagonal, done. So yes, the row swap and the row addition, these are powerful, simplifying. 3 tools, I mean, those are the basic tools. The transpose, the row swapping, the elementary row operation tricks, and the cofactor expansion. That's pretty much it for calculating determinants. That coupled to the product of the diagonals for a diagonal or a lower or upper triangular matrix. That's pretty much all I know. Yep.
So the diagonal rule also works even if the top isn't cleared out?
Yes, yes. That was I was about to say is diagonal or upper triangular or lower triangular all have product of the diagonals is the determinant.
Because you could clear them out if you did more row reduction.
That's a good way to think of it. Is I could do type 3 row operations, and the backwards pass would just clear it out. Yeah. Or I would have a 0. So anyway, yeah. Not a bad idea. All right. Well, anyway, I have gone way over. Actually, technically, I think I went 2 over because I started 7 minutes late. So, sorry. I'll shut up. You don't have to go home, but you can't stay here. It's a saying that people say. What's that? Actually, you could stay here, I think.
All right.
If you want. I don't recommend it.